We start with a curve in a loop. This is from high school, I guess. First of all, sum of currents is zero in a network of conductors. So I1 plus I2 is I3. This also means that if you only have one wire, with any current coming in, will have to go out, otherwise it will charge up the node. If it doesn't, it will have to go out, it will have to go back. See? All currents are in loops. Now there's an extra story to that, we get to that later maybe, but for the moment all currents are in loops. So they must have a return back. And if they have, find it. Okay. Where is the return current flowing? That's usually the problem in equipment that's not working. They didn't look at it, or they assumed it would be okay. They have a digital design system, you know, this PCB designer. You don't even show the power lines. You show the ICs and the interconnection of the inputs and outputs, and then the system will take care of the power. But if it's nasty, you should look at those too, and you should know where these currents are flowing. So it's important to know at least the problem is there. Okay, we'll show it with this experiment. I think this is the most simple experiment we have. It's what? But I told you, you see it was easy. Frank said we should do everything with these buttons and you can click it very fast. I said, yeah, but the audience needs time to assimilate whatever I say. So whatever time it takes for me will help you to better understand the story. Okay, this is a loop, right? I use the same generator. I'll do it like it's drawn there. I'll have to switch this off a little bit, otherwise the oscilloscope won't work. This is a 50 ohm load. Channel. It's there. Yeah. It will work for 5 volts, okay? Now, a little faster. You see there's a little difference between A and B. See? You can see it already here. This is spikes, no one doesn't. A little faster. You see it better, right? So, okay, the bottom is A, which is coming from the generator. This is my while loop. So the current is flowing from the generator to the T-junction, then to this metal plate. The inner wire goes in the red one, back in here to the load, and from the load the return path is through this coax, through this metal plate, and then this coax. Okay? So this is actually the open part of the loop, the rest is flux. And you see that the A signal has a spike and B doesn't have it. How does it come? Well, this is a inductor. It's a coil. Run by a coil. Okay, an inductor. For an inductor to flow, for current to flow, you need magnetic flux. Or magnetic flux means you can have a current. That's in the Maxwell equations. Something I won't tell next week either. And the Maxwell equations say that if you want a current, you need a current, you need a flux. And without flux you cannot have current. So you have to build up this flux, which takes time. So before there's any flux there, the generator will just go from 0 to 5 volts. Boom. And no current. As soon as you have current, this thing is 50 ohms, this is 50 ohms, so this part is 2.5 volts. 2.5 volts is the equilibrium, right? Usually it goes to, actually to 5, but then the scope is too slow. You can make the scope faster, but then it will not look as nice, but this is actually what it should be. So what's called the resolution enhancer on the scope. It does enhance the resolution, but it reduces the bandwidth. Okay. So now you have a fast rising end. Takes time to get current, and when there's no current in the line, there will be no current at the load, right? So this is just as slow as this goes. This edge looks like this one. It's inverted. Okay, so it's very simple. Right, but you can see that you need the flux. Now what can we do? We have seen the loop, this is the loop. We can make it small. And make the loop smaller, and you can see as the effect gets less, right? You can do it in a different way. Metal plate. And put a wire on the plate. See? This is called, you can get it completely zero. You see, it's very difficult to get a loop small enough if you have a fast signal. This is about 2 nanosecond rise time. So it's difficult, but you can do it with this, okay? What you probably should do if you have something like this, you should use stereo cable. Okay, right. And now get to the next. And that is that you have delay, right? So I can get this back. You see there's a time delay. The time delay between signal A and signal B. That's because there's, well, in here, half a meter, 1 meter, 1 meter, 1 meter, 300 meters. 300 meters of line give you a delay. Now, delay you cannot explain by telling that current is running in loops. The old-fashioned idea of pushing the electrons, and then after some time the electrons will come back out at the other side. So it's not working like that. But that's the difficult part of the story. We get to that a little later. But okay, you have time delay, but at least you have gotten rid of your spiking. You can use any of the other cables. This is the wrong cable, right? And you see the spike back, right? And the spike is what you hear on the radio. That's the build-up of flux, removal. Then you can hear on the radio. Should I have it here somewhere? No, yes, maybe here, yeah. I should moderate it. Interesting part. Something else is leaking here. Oh, okay. Officially, this part should not make noise. But okay, it does. You get it a lot during demonstrations. Something doesn't work. Advertise it. Okay, so. Okay. So, that's the running loops. Let's see, to have my presentation back. There it is. Okay. So, to get the current running here, you need flux, and it takes time to build up the flux. You make it small. The spiking gets less. It's going a little bit to get less. So that's one way. The other way is to use a metal plate. Okay. So, do you have a current? This is actually my wire. This is the point of the arrow of the direction of the current, and then it's the right hand screwdriver law that tells you that magnetic field will be in this direction. If you want to know how much, you know the current, you can estimate using the Buesink law, sometimes called Ampere's law. The current divided by the circumference of the circle at distance r from the center. If you want to know the flux, you have to integrate. That's also something which is not so suitable for next week. This is of course the return current. if I assume it's just one loop, this current should be the same as this, and the arrows will go in the other direction. Let me just again turn the screwdriver or corkscrew to get the direction of the loop. Then we go to, if we can animate what happens. If you have two wires, but for you that are going to do this, radial lines will give you a moire effect looking like the magnetic field, and if you have circles it looks like the electric field. You get rid of it. So if they are right on top of each other, no field. That would be the coax situation. You turn signal going in the same direction, same line, no field. But if they are a little bit separated, you'll always have a remaining field. Okay? Will never go away. So the twin wire will never be quite silent. There will always be some magnetic field around it. You cannot get rid of it if you don't put them on top of each other. So this we should still do, I think. Slow edge. We should have a slow edge or something. There is a slow edge in this machine. No. But it's not working. So remember that. But this is the slow edge. What we did is there's an output. It has built-in 50 ohm impedance, and then we put a capacitor on the end of that line. So we have a line in PCB to the output, and you can switch the capacitor. The capacitor is here, the switch is there, so it's back and forth about 10 centimeters, which is too much. But it never worked for this machine. Maybe this is better. It looks the same, right? Now it's so slow. I have to change the trigger. No? Ah, okay. There it is. I think this is high-speed CMOS, which is running on 3 volts. So that was a little less. But the spiking is very low now. It's slower. Maybe 100. Okay. Okay. I'll shift it down. Oh. See, if the edge is slower, you don't have this spiking effect. Stroke should go faster. I can see it a little bit, right? So, so spiking and then slow. So slow, it gets smaller. Now keep looking. I think I should have the generator somewhere. Slow part is not working today. Later. Okay. The idea is that it is low, the root is down. Not have the spike, but slow it. You can use an ordinary generator, it's usually very big. Okay. So use the slowest possible logic. That's one of the basic rules for ABC. If you don't need high speed, don't use it. Well, this is too fast. Stairs would be maybe nice. Which is also something I don't need to do next week, I think, because it's about reflections. Late part. Now I'm going to remove the load. So now we're coming. Generator. That's what you see here. Generator, channel 8. Where that's there. The cable is 50 ohm. So during the time it takes to get from A to B, it will look as 50 ohm to the cable, to the generator. Then when it gets to B, hey, no load. So there's a flow of current going there, feeding the 50 ohm, and at some point the 50 ohm is gone. So it goes to double pulses. Reflection, you get a reflected wave. The reflected wave is getting on its way back to channel A. It takes the same time, of course, to get back to A, and then boom. So if you put your time gauge very slow, you maybe wouldn't notice it, but it's there. If you use a generator, and it's not loaded with 50 ohm, you have these effects. But okay, that's the transmission line. And again, this is very difficult to explain when you use the metaphor of electrons flowing over a wire from out of the in. Okay. Okay, we get to the second Kirchhoff law, whereas the current law is the voltage law, which tells us that the sum of voltages in a maze network would be zero. Well, okay, is that true? Obviously not, otherwise I would. Then we get to Faraday's law, which is not taught at high school, I think, which tells you that the voltage in this loop would be the change in flux divided by the transition time. So even if this is a fixed voltage, if it has some area here, then the change of the magnetic field lines inside that area divided by the time it takes, it gives you a voltage. It's called d phi dt, change in flux at the time it takes, or you could write it in the frequency domain, which is the omega times the flux. Both ways you can use, because the equation is formally not right, but okay. This is the frequency domain, this is the time domain. Okay, the minus sign tells you that the voltage will be opposite to actually that voltage would generate a field which is opposite of the flux that is changing, so it tries to oppose the action. It gives you a minus sign. And it helps because you can use it. You'll see that later. Okay, so Faraday's law. That's the idea. You measure, you have a loop. If you change the flux, you get, during the change, you get the voltage. Okay. Now, that's the next step in the story. You say, okay, now if we have a loop, with some current in it, changing current, varying flux, you bring in another loop. But some of this flux obviously would pierce through the second loop, right? So you make a flux with the first loop and the second loop. Now, this is the definition of inductance. Flux divided by the current. So you have some amount of flux. You divide it by the current that produces it, and you get the inductance. And to make it easier, we have machines that do it for you, so you can connect your power and measure the inductance. It gives you in henries, right? Then this, the second loop, has some of the flux, maybe not all. But there you can define a neutral induction between this loop and this loop, which is the flux in the second loop divided by the current in the first loop. So the only difference, you see it's the same dimension, flux divided by current, right? This is henries. This is also henry. Same dimension, but this could be a smaller number, this one. So if these loops are not quite matching, then not all the flux will be in a second. So we'll have a little, it should be a little smaller than this one. The largest value you can hear is the two. When you put them completely on top of each other, all the lines are going to both coils, and then L and M are equal. But usually this one is a little smaller. We call this machine a transformer, and it's used extensively in the electric business. So Everybody should know it. Okay? Now for EMC purposes, we're trying to get as little of this as possible. So you don't want to lose flux, and you certainly don't want to pick up flux unless you're doing the transformer. For noise fields, this loop should make as little as possible. So no current will be okay, very small loop will also be an option. Second loop, same thing, make it small, the smaller it is, the less it will pick up. And then remove them from each other. So this one should be here, and that one should be over there, and that's probably okay. Now, we're looking at this neutral induction. You can write it a little different. I just putting that there and there. Flux, calculate M times R. The flux in loop 2, that's the one that's important for us because that's the one that will create our noise. Our noise voltage over the detector. And then Faraday's law says, okay, this noise voltage here, C, is d pi dt, right? Or the omega times this flux in the second loop. With the minus sign, okay. And then you can model this. So you have this actually a model to tell you what you can expect to get out if you have this combination, this M and L. And the current over there, and this is the equation you get. The noise voltage is the omega times M12 times the current in the first loop. Okay? This is a model for this. They call it substitute source. They use it a lot in when you want to evaluate a crosstalk situation, interference situation. So you make a substitute source. For a magnetic system, who coils, you get a voltage. For an electric system, later you'll see, you get a current. A substitute current source. You get a substitute voltage source. Okay? This could already be too difficult for the group next week. Okay, this should be easier. Now we can make a situation with two wires. You get something done. That's my other long wire. Well, that's something if you do experiments. Have some backup for all kinds of stuff. So if you just run coils on one line and run everything, and of course at some point there will be one wrong or lost, or trying to find it. So I have 4 of these in the box, just in case. Two of these. This is again, Frank would say, it could be done faster with a different type of devices. Instead of screws, you can use these clip things. So now we have almost the system in the picture. So loads at the end of the wires to get current. To remove them, then we have more voltage, so the capacity. Now it's inductance. So loads at the end. Oscilloscope, source, this side. By the way, this generator T-junction and then something itself is the setup of the time domain reflectometer. Okay, we have one on the left, very fast one with 50 picoseconds per time, something like that. Look at this is slower, but you can do time domain reflectometry with this. Also something I won't tell. So this is okay. You could, of course, just put the scope here and then have this go out and then take it here. But to get some triggering, you usually want to measure. You can measure it there, then you have delay. So this is easy. Okay, setup is there. So let's go. Okay. So now, this should be more. Okay. So there's a difference in A and B now. A is the normal 2.5 volts level over there, and B is a little more sensitive. But this is the spike, which is actually crosstalking from the red line to the green line. Okay? Now on the red line you see the spike. Of course, because the generator at this side. This is the generator side, that's what we're measuring. You get the same spike. If you measure it here, it will be flat. Okay, remember that previous exercise is just built in here too. Okay, now we have crosstalk from A to B. So what can we do? It looks small, right? So when this looks small, it helps. That's it. Now look. If this looks small, it also helps. Now what should we do? Make both look small, right? Now that's difficult. Because now, can we help? So hold this here and make it look small. Okay. But it doesn't go away, right? Because it's very difficult to get both look small and get the green and the red as far separated as possible. That miraculous invention, the white metal for EMC. And now, put it from here. Yeah, just make contact with that. Yeah, like that. But now, you can you see it's better, right? Better than this. The white metal helps. A slow edge would also help. I get too small, I don't know. Maybe this is the wrong generator. And this one is not so good at making slow edges. It will do something, but not modulated, so this one should be the slow edge. See, it doesn't work. It's stupid. An error in the PCB cannot be credit. It doesn't do. Okay. The slow should help. What do we else we have? Let me see. Okay, this is the initial situation, the crosstalk. You notice that only the changes, yeah?
Who left the black circuit? Who left the black circuit?
This?
Yeah.
You can calculate, we get the equation later, but the idea is that you can have each loop small by, now obviously the return conductor is this plate, right? By putting the wire against the plate, and use this wire against the plate too, and then keep them at some distance, centimeters. How much distance we get to later. You can calculate. But you can actually calculate how far you should separate two traces on a PCB to get some amount of reduction. Which also in France sees this, that's a little difficult for this group, for the groups next 3 times. Okay, so only the changes in flux will produce crosstalk. During this change, you see it, and then it's quite easy. Well, slow helps. We didn't quite see it, but it helps. But of course, everybody will do it as fast as possible. So the slow option is usually not in the story, but it does help. Okay. Now often they say, okay, this wire in between, it's the common return for both loops, right? They call it the common B. And if it were a resistor, it would be nice. It's okay, it would be in series. A resistor which would be here would be in series with both loops. And any voltage over the resistor you would see in both loops. For inductance, it's a little more difficult. Actually, inductance is actually a loop, can never be a wire. So the loop is the inductance. There's inductance here, there's inductance here. You make that small. So this is the one trick we did. Both wires, but then of course they're getting fairly close to each other. Even if it would be cables, it would be difficult to place them in the system, that they would stay in that position during their lifetime. It's another thing you have to think about. This is better, because there's so large distance between them. They call this a cable tray, by the way, this metal thing. You see them in the corridors and all covered in the ceiling. Okay? What happens is that this return current for the red wire, in this case the source, will go under the wire. We'll try to squeeze under the wire. Why? Because it's easier for the current to flow if there's no inductance. If there's a lot of inductance, it takes time. And there's no time, because you have a transition, and if the current can go back, it will take the path of least impedance, they call it. So this is the path of least impedance, will be under this wire. And the lower you get the wire, the narrower this area gets. So anything left over here of this tail, and this distribution here, is the neutral induction. So if you bring them close together, you'll see that. But usually some wire for PCB trace, they say, okay, three trace widths separated would be reasonable if the traces are of the ground plane, of course. ground plane is actually right in the speed. Exactly.